In this video about special relativity, I'd like to show where the velocity addition formula comes from, and also the relativistic Doppler shift. The Doppler shift will come after doing the velocity addition. In order to do the velocity addition, it's helpful to think about a new thought experiment. And in this thought experiment, it's a special piece of apparatus. And it's really similar to the thought experiment apparatus that I referred to in the previous video as the light clock. But this one is interesting because it involves both light but also particles, like little material particles. So an example could be, honestly, a little water molecule or something like that. It could be an automobile, but an automobile is kind of a big thing. So something small, like a water molecule, or even like a small pellet or a grain of sand or something like that. Doesn't really matter what it is. But the point is this is the apparatus. It's got 4 parts to it, and the 4 parts are a particle source, so that's right here, and the particle source is the place where one of these little particles can come out of. It's shot out, and the idea is it's given a speed v, and this speed v is relative to the apparatus. So you might imagine that this apparatus is actually kind of rigidly separated so that the interfaces are a separation distance L apart, and this particle source shoots out a particle with a given speed v. And it travels across to the particle detector and is detected. And there's a special feature of this piece of apparatus a light particle is emitted at the same time that the particle detector receives the particle. So the idea is, as soon as the particle hits the detector, at the same moment in time, a photon or some light is emitted. So at the same instant. So particle travels across, and as soon as it touches here, a photon comes out, or some light comes out. And then, of course, it gets detected by the light detector. So that's the 4th piece of the apparatus, right? So a particle is emitted, travels across at the speed v. As soon as it touches the particle detector, a photon is released in the opposite direction, travels across, and is detected at the light detector, which is at the same location as the particle source. So the detector and source are at the same place over here, and the source and detector, same place over here. Separation is given by L. Okay, so let me redraw this particle in the middle somewhere, traveling at the speed v, and I'll take away this. So light emitted here, or something like that. Anyways, I think you can see how this plays out. So this is the new thought experiment apparatus. And so I'm going to put this apparatus into an observer frame. So the apparatus is at rest in O prime. So what I'd like you to have in mind is the following picture. So this is observer frame O, and this is observer frame O prime, and the apparatus is at rest in O prime. So I'll put the apparatus in O prime, so it'll be P, S, L, D, and then PD, particle detector, and a light source, separate by a separation distance L. So the apparatus is at rest in O prime. So O prime can measure what's known as the proper length. Right? So that's what L prime can measure. Also, when the particle is traveling across, this little thing has velocity v, but it's v as measured by O prime. So v prime is velocity of particle according to O prime, right? So L prime and V prime. So an interesting thing is, so delta T prime equals the time between particle emission and light detection, right? So the particle is emitted, and then it takes a certain amount of time for the particle to cross the gap, and then as soon as the particle touches the detector, immediately a light signal is sent away from the light source, and takes some more time to go at the speed of light across the gap distance to the light detector. And that total time is delta T prime. And I bet you can, it's easy to see what delta T prime is. So the particle travels at the speed v prime across the distance L prime. So that's the time for the particle to make the outbound trip is L prime over v prime, plus the time for the light to cross at the speed of light the same distance. So same distance, but at the speed of light, right? And that's the total amount of time for the trip. It's in terms of a proper time, because the single clock located at the particle source and light detector, those are located at the same place. That single clock located there can measure this time. So it's a proper time. And the L prime is the proper length because the apparatus is at rest in O prime. And of course, O is going to measure, so O measures a length, which is a contracted length, so 1 over gamma, right, the gamma factor as a function of the relative speed of the two frames of reference. So O prime moves towards the right, or in the positive x-axis, or however you want to say it, but O prime moves toward with speed u within O. So this is 1 over gamma of u, and then you multiply by L prime. And then what O also measures is a delta t, which is equal to gamma of u on top, so the gamma factor is on top, times delta t prime. Right, so O is going to measure two different pieces of information. But here, L prime would just be the size of the apparatus, so you could measure that with a ruler inside of O prime, and then delta t prime is this thing that you have to use a clock to wait for the round trip signals to happen. So the question is, what does observer frame O measure for the speed of the particle? So in order to answer this question, what we have to do is basically just think about what O is going to see happen. And remember that the connection between O and O prime is given by length contraction and time dilation. So let's be really careful and think about how O watches the little particle. All right, so the way that ends up being the best way to do this is to pay attention to what does O measure for the time for the particle to go from the particle source to the particle detector plus the time for light to go from the light source to the light detector. So let's say this is delta t for the particle plus delta t for the light. All right, so delta t for the particle. So let's think about this. So the particle starts from the particle source light detector. So here's the particle starting its trip, and it's going to, according to O, right? According to O, not O prime, it's going to have a velocity v. And this is the velocity v relative to O, right? So this is the velocity that O would report for the particle. So it's going to begin its trip towards the particle detector and the light source thing, crossing a distance L, right? But the problem is this entire apparatus is also headed towards the right inside of O, because don't forget that this machine or this apparatus is at rest in O prime, and O prime moves with speed u inside of O. Okay, so what this is going to do is that during this time for the particle to make it to the particle detector, the problem is everything has shifted over by a distance. Right? So this is just like what happened when we were talking about length contraction, actually. Just like in length contraction. So the particle starts here, but has to make it all the way to there for us to determine this time. So this time for the particle to make the outbound trip is equal to, so it's a distance per speed, right? And the speed that the particle uses is the speed v. That's the speed seen by O. And the distance is L plus the fact that this detector, this particle detector, has shifted over by a distance that's equal to the speed u times this same time. So it's weird because the time is defined in terms of itself, right? But you can solve for the time. So v delta t sub p equals L plus u delta t sub p. So this implies that delta t sub p equals, so the u is going to be subtracted from v, and it will go underneath L. So L is v minus u. Pretty sure that's correct. Yeah, I think so. Anyways, so this is the time for the particle. It's in terms of L. That's the particle's outbound trip. So the time for the light, though, is sort of similar. So it's also a distance divided by a speed But since light travels at the speed of light, according to Einstein's postulate, it's the same speed for any observer, any inertial observer, O, and O prime sees the same speed, but we're talking about O right now. But the distance is interesting because at this moment in time, the light particle is sent out, but the problem is as the light particle makes its trip, the light detector advances on it. So the distance is only this far. That's how far the particle has to travel. So it's not all of L. It's L shortened by the fact that at the speed u, this light detector advances on the light particle. So it's in the small, short amount of time, delta t sub L. So again, you can solve for delta t sub L. So, actually, is that, yeah, so just like we solved for delta t sub P up here, delta t sub L. So is going to be, so you multiply the C up and then add the U delta T over. So C plus U is underneath L. So L over C plus U. So that's the delta T sub L. Okay, so, all right. Yeah, so now delta T, as measured by O, which is the combination of the outbound particle and the inbound light, is equal to, so it's L is common, so I'll just go ahead and take it out, and then it's 1 over C plus U plus 1 over V minus U. All right, so now back from before, I have this delta T prime. Right, so this is in O prime's perspective. This is O prime data. And this is O data. And you can see that there's no primes for O, and there's only primes for O prime. And what's more is we get to use length contraction and time dilation. And this gamma of U, this U and this U is the same. And what you can do, it's a big old algebra exercise. Is you can get the following relationship. You can get that V, which is the velocity of the particle as measured by O, is equal to V prime plus U divided by 1 plus V prime U over C squared. This is what you can get. And this is called the velocity addition formula. So this is, it's not necessarily straightforward, but it's not that hard. Maybe it takes 1 page, right, of careful math. The thing is there is no more physics to do. You use length contraction. Here's some relationships between O prime and O data, and O prime and O data in the time dimension, and this is the space dimension. And these are further relationships between delta t and this thing called V, right, and delta t prime and this thing called V prime. And what we ultimately want is a relationship between V and V prime in terms of pertinent information. So the other information is U. This is the relative speed of the observation frames. And also C. This is the speed of light. Okay, so yeah. To study the relativistic version for the Doppler effect, which is a it's an effect on the frequency observed by a detector. We'll be doing the relativistic Doppler effect for light, but over here, if you remember what the Doppler effect is for sound on air, it depended on some details. It's, for example, speed of the emitter on the medium, and it also depended on the speed of the detector or the listener on the medium. So there were actually two speeds. There was like the speed of the emitter relative to the medium and the speed of the detector relative to the medium, and the Doppler effect depended on both of those velocities. There is no medium, right? This is the no ether hypothesis, or actually, yeah, that's a funny thing to say. It's more like the ether idea was the hypothesis, or I'm not sure what to say. But anyways, there is no ether. So that means there is no sort of preferred reference frame. So the only dependence for the Doppler effect can be, so the only dependence can be the relative speed between the emitter or source of the light and the detector. So we'll say that the emitter is called S, and it's just going to spray out some light waves, and there is a detector called D. And there is a way to view this picture when the detector, say, is moving away. We're gonna do the thing where they're separating. So the source is standing still and the detector is moving off to the right away, or the detector is actually standing still at rest and the source itself is moving away at the same speed, right? So these are the same thing. I want you to recall, though, if the source is moving away, then it's going to effectively spread out, right? It's going to spread out the wavelengths that the detector sees. If instead the source is standing still, like you have the above picture, then as the detector is being bombarded by these light waves, it's advancing along before the next light wave can reach it, right? So that sort of increases the time or slows down the frequency between wave crests for the detector. But both of these pictures need to give us the same answer. Okay, what's interesting though is in this picture, it is true that the little light wave fronts move at the speed of light, but it is also true that in this picture, these light wave fronts also move at the speed of light. And this is a postulate, right? Einstein postulate, that regardless of the frame of reference in which you're watching the stuff happen, light is going to travel at the same speed. That's the weirdness of relativity. Okay, so what we're going to do is we're going to have a bit of a twist. The twist is, so we're going to put proper time measurement in O. So the reason why this is a twist is because we've been giving the proper time to some stationary device in O prime. But now we're going to imagine the stationary device to be actually in O instead. Okay, so here are two pictures. Here is a picture of O, and there is a source of some light waves, right? In fact, if you want, this is one wave, right? Between crests is one whole wave. Here's a second wave, a third wave, and a fourth wave, because just creating the beginning of the fifth wave, but it hasn't been created yet. So there's 4 waves here. And in this picture, we have O prime moving towards the right. But the thing about O prime is it's the rest frame of the detector, right? So this picture right here looks really similar to here. But we can alternatively have the point of view where we have the source S, which is at rest in O, but we're imagining O receding, right, from O prime, or the detector in O prime. So the detector is in O prime, and we imagine O prime as being the rest, the thing that seems to be at rest. And this looks more like the second case here, right? So this looks like case number 2, and this looks like case number 1, right? Yeah. So, okay, so that's our setup. So what we're going to do is we're going to say that during time interval delta t, and I'm going to put a sub n waves are created, right? So during this time interval, they are created by the source S. So because the source S is at rest in O, this time right here is proper. This is a proper time. Because in a sense, like, yeah, you can use a single clock. It's a clock at the source, and that clock at the source measures out this time, and it's the time to watch 4 wavelengths. For example, in this picture, it's the time to watch 4 wavelengths get created. So it's the proper time, delta t sub n. Okay, so that's delta t sub n, and this delta t sub n, furthermore, is equal to, it turns out, it's n times, say, the period, right? This has a period t and a frequency 1 over t. And because we're talking about the proper time in this case, you could maybe say that's called the proper frequency, right? Furthermore, because these wavefronts move at the speed of light like this, you can also, I'll remind you, say that there's a basic relationship that the wavelength is equal to the speed of the waves divided by the frequency. This is a basic wave relationship here. Okay, so yeah, so back over here, this is n divided by the frequency, right? Okay, so what we're going to do next is think about O prime. This is all for O. So what does O prime see? So we're going to take the point of view of this picture over here. Okay, so what does O prime observe? So O prime will measure a non-proper time. This is a delta t sub n, to sort of count n full waves. And actually, I made a mistake. This really is a time interval delta t sub n prime. It will be measured in with O prime, and yeah, and you'll have to use, actually, if you think about it, you're going to have to use multiple clocks, because what O prime needs to do is actually watch this source recede. So the beginning of the 4 wavelengths happens at a different place than the end of the 4 wavelengths. Yeah. So that's kind of a strange thing to say. That's why this is not a proper time measurement. But O prime is going to use multiple clocks, that is, clocks in different locations inside of O prime, to measure out this delta t sub n prime to count n full waves. And we can make a judgment call on how much time this is according to O prime. So let's figure out how O prime will predict it, right? Okay, so here's what we have to do. So this is kind of strange. Let's see. So here is at the beginning. Yeah, the source is a little bit closer, right? Because the source and the detector are receding. So the source is here at the beginning of, so first creating waves, right? So this is the beginning. So there aren't any waves created yet, and here is the detector. But this thing is receding, and it's receding at the relative speed between O and O prime, right? So here is the first wave. So that first wave, in the space of time delta t sub n prime, that wave is going to travel all the way to here. So this distance right here is the speed of light times that time interval to count n full wavelengths. But what happens is by the time it finishes creating all 4 of those waves, for example, this thing will have moved back to here. So here is the location of the source at the end of the delta t sub n prime. And this distance right here is the distance that the source travels during that very same time interval. And so this distance in total is a capital D. I'm going to call it capital D sub n, and it's a prime because it's the distance that would be measured by O prime. And this distance is the summation. So it's C plus U times delta t sub n prime. So what's interesting about this distance is it is n times the wavelength, where the wavelength would be measured by O prime, right? Up here, this is, for example, n times the wavelength, but it's the wavelength as measured by O, right? So that's the wavelength that's measured by O, because this is a drawing such that the source is standing still. It's the rest frame of the source. So that distance right here is equal to the distance as measured by O, so there's no prime. But over here, this is the distance that those 4 waves, for example, this picture, take up in this picture over here, because the 4 waves occupy a sort of a larger space, according to O prime. Okay, so that means that this lambda prime is equal to, right, I can solve for it, it's d prime sub n divided by n, so this is c plus u times this delta t prime divided by n. Sorry, I got a little confused, actually, and started to go down a path with my thinking that wasn't going to help. So I stopped recording, and so let me put some stuff down that's going to take us towards the answer here. So in O prime, we have that there is a wavelength that is this distance that I calculated for you earlier divided by the number of waves in that distance. And the the solution to the problem, it turns out I had to go and look in the book for a little bit and re-remember how things go. But anyhow, so the solution is in O, there is a time that I mentioned earlier, and this is the time to count out some number of wavelengths, and this was equal to n divided by f. And so the point is I'm going to multiply this f up on this time measurement like this to get n, and then I'm going to take this and I'm going to put it right there. Right? So if I do this, what's interesting about this is n is a counting, right? And if O counts out 4, then O prime is also going to count out 4. So that's kind of interesting. That's something that O and O prime will agree on, right? The number of waves. They may not agree on the frequency or the wavelength, but what they're going to agree on is the number of them, right? So that's kind of like considered a scalar or an invariant. But anyways, n is a counting, so O and O prime will agree on value of n. Okay, so here is n. Here. So let's put this right there, and so lambda prime is equal to c plus u times delta t prime divided by f times delta t sub n. And the reason why this is interesting is because the bottom is all information or data from O, and the top is, in a sense, all information or data from O prime. So what we're going to do is two things. So lambda prime is equal to c over f prime. This is just a basic relationship about waves. I brought it up before. Here's what it looks like for data from O. This is what it looks like for data from O prime. And O prime agree on the speed, right? Because that's Einstein's postulate. All the inertial observers are going to agree on the speed of light. So that's one piece of the puzzle. So over here, I can just say that this is the same thing as c over f prime, right? That's what lambda prime is. Another thing of interest is actually the relationship between delta t sub n and delta t sub n prime. I've been forgetting the lowercase or the capital n's. This is the time interval associated with an n number of waves. So it turns out that, so remember, O measured proper time. That is, this was the proper time. That means that delta t sub n prime is gamma factor away from delta t sub n, right? That's the proper time in this twisted case. I mentioned that there's a twist. So what this means is exactly this. So let me just put this over here. Delta t sub n prime equals gamma of u delta t sub n. So what these two things do is they give us that c over f prime is equal to c plus u divided by f, right? And then delta t sub n prime divided by gamma of u delta t sub n. Oh, no, excuse me. Shoot. Not that, right? C over f prime is equal to c plus u. I was going a little bit too fast. The top is that prime right there, so it's gamma of u delta t sub n divided by f times delta t sub n, which means that, in a sense, what we're discovering right here, the actual amount of time that the source emitter or the emitter is emitting light waves doesn't actually matter, right? So that's an independent issue, it turns out, because it divides away. And what we're left with is, if you flip both sides, well, actually, I'm just going to be a teacher and say, after some algebra, where you take this gamma factor and you sort of re-realize what it is, what you can get is that the frequency as observed by O prime is related to the frequency of the source as measured by the source, or in the rest frame of the source, times the C minus U divided by C plus U. So this is for source and detector separating. Right? So the source and the detector are separating. You know that if an ambulance is running away from you, you hear its frequency downshifted. So the frequency heard by the detector is smaller than the frequency emitted by the source, right? So that's the case for separating. It's left as exercises and homework problems to think about, what do you get if instead the source and the detector are running towards each other?